So now I'm going to look at three-dimensional geometry. In particular, I'm going to look at an introduction to volume and surface area with some applications. And then I'm going to go over a lot of formulas for volume and surface area. So let's start with an introduction to surface area and volume. I'm going to start with an application of volume. A shipping company produces boxes with a capacity of 8 cubic meters. What are some possible dimensions for the boxes? Well, one possible size is 8 meters by 1 meter by 1 meter. 8 times 1 times 1 is 8. Meters times meters times meters is cubic meters. Another possibility is 2 meters by 4 meters by 1 meter. 2 times 4 times 1 is 8. So we have 8 cubic meters. Another possibility is a cube, where each of the edges is 2 meters. 2 times 2 times 2 is 8. So we have 8 cubic meters. Now I want to look at another example. Candace is building a new swimming pool in her backyard. The pool will be 16 feet by 36 feet by 4 feet. How much water will be needed to fill the pool? And how much tile is needed to cover the sides and the bottom of the pool? Well, let's start with a question about how much water will be needed to fill the pool. This is like our shipping box example. This time, our dimensions of our pool are 4 feet by 36 feet by 16 feet. So if we want to find how much water is needed, we need to find the volume of this figure. So we would take 4 feet, multiply that by 36 feet, and multiply that by 16 feet. And I'm going to pull my calculator out to figure this out. So we have 4 times 36 times 16, which is 2,304. And we're multiplying feet by feet by feet, so we get cubic feet. So Candace needs 2,304 cubic feet of water to fill her pool. Well, now let's turn to the question about tile. Candace is going to cover the sides and the bottom of the pool with tile. So looking at our pool here, we have 2 long sides, 2 short sides, and the bottom of the pool. Let's lay this out flat. So we've got our bottom, 2 long sides, and 2 short sides. If I want to find the area of the bottom of the pool, which will tell me how much tile I need to cover the bottom of the pool, I need to take 36 feet and multiply that by 16 feet. That gives me 576 square feet. If I want to find the area of a long side, I need to take 36 feet and multiply that by 4 feet. That gives me 144 square feet. And if I want to find the area of a short side, I need to take 16 feet and multiply that by 4 feet. That gives me 64 square feet. If I want to find the area of the entire pool, I need to add up the area of the bottom of the pool 2 times the area of a long side and 2 times the area of a short side. So that's 36 feet times 16 feet for the bottom of the pool, plus 2 times 36 feet by 4 feet for the 2 long sides, plus 2 times 4 feet times 16 feet for the 2 short sides. When we do that computation, we get 992 square feet. So Candace will need 992 square feet of tile for her pool. Now let's look at some definitions. Surface area is a measure of the boundary of a 3-dimensional figure. The boundary of a 3-dimensional figure, or the sides of a 3-dimensional figure, are 2-dimensional. Surface area is measured in square units. For example, square meters, square centimeters, square feet, or square miles. In the pool problem, I didn't actually compute the surface area because their 3-dimensional figure was a rectangular solid. I didn't consider the top of the pool. I wasn't going to tile the top of the pool and close that in. Volume is a measure of the space enclosed by the boundary of a three-dimensional figure. We computed the volume to figure out how much water was needed to fill the pool. Volume is measured in cubic units. For example, cubic meters, cubic centimeters, or cubic feet. Volume can also be understood as capacity and can be measured in liters or gallons, for example. So I could have asked how many gallons of water are needed to fill the pool. Now let's look at some formulas. Starting with a formula for a rectangular solid, if L, W, and H are respectively the length, width, and height of a rectangular solid, its surface area S and volume V can be determined using the following formulas. The surface area is 2 times the length times the height, plus 2 times the width times the height, plus 2 times the length times the width. With the swimming pool problem, since I didn't consider the top, I only took one of the lengths times the widths to give me the bottom area of the pool. And then I took the two long sides, that would be 2LH, and the two short sides, which would be 2WH. For the volume, we just take the length times the width times the height. If we have a cube where all the sides are the same size and the length of a side is E, its surface area S and volume V can be determined using the following formulas. The surface area is 6E squared. We take the area of one side, which is E squared, one of those squares, and multiply it by 6 because there are 6 sides. For the volume, we take the length times the width times the height, just like a rectangular solid. But in this case, the length, width, and height are all E, so we have E times E times E, which is E cubed. And we're looking at a cube. E cubed, a cube. If we have a sphere with radius r, its surface area S and volume V can be determined using the following formulas. The surface area is 4 times pi times r squared. The volume is 4/3 pi r cubed. If we have a cone with base radius r and height h, its volume can be determined using the following formula. The volume is 1/3 pi r squared h. Notice we're talking about the base radius. The base doesn't have to be at the bottom of the cone. In fact, the way this cone is drawn, the base is at the top of the cone. But that base has a radius r. Now I want to look at an example. Find the surface area of a can of corn with radius 1 inch and height 4 inches. To think about how to find the surface area here, I'm going to think about the boundaries of this can. So I know that I have a circle at the top of the can and a circle at the bottom of the can. Well, what I'm going to do is cut my can vertically and then lay it out flat. When I do that, I get a rectangle. And then the top and bottom of my can are circles. So let's lay those out flat too. Well, I know how to find the area of a circle, so I'm not going to have any problem in my surface area formula finding the area of the top and the bottom of the can. I also know how to find the area of a rectangle. Well, in this rectangle, I know that the height is 4 inches. What I'm worried about is what is the length of the long side on this rectangle? Well, I have to think about where did that long side come from. Before I cut the can vertically, I had to cut off the top and the bottom. I had to cut around the circle. And so on my can of corn, I'm cutting around the circle, and what I get is that the length of the long side of the can of the corn is the circumference of the circle. To find the circumference of a circle, we take 2 pi times the radius. In this case, we know that the radius of the can of the corn is 1 inch. So this would be 2 pi times 1. We know that the height of the rectangle is 4 inches. That was given to us. That was the height of the can. So when I go to find the surface area of this can of corn, I'm going to need to add the area of the rectangle and add 2 times the area of a circle, since I have the top and bottom of the can. So I'm going to take the area of the rectangle and add 2 times the area of the circle for the top and bottom of the can. That will give me the surface area of the can. Well, we just found that the area of the rectangle was 2 pi times 1 inch times 4 inches. And the area of the circle, since the radius is 1 inch, is pi times 1 inch quantity squared, pi r squared. If I take 2 pi, multiply it by 1, and multiply that by 4, I get 8 pi. If I square 1 and multiply that by 2 pi, I get 2 pi. 8 pi plus 2 pi is 10 pi. And I have inches times inches for the rectangle, and I have square inches for the circle. So I end up with 10 pi square inches. So the surface area of the can of corn is 10 pi square inches. Well, let's look at our formulas for a circular cylinder. We just developed one of them. Given a circular cylinder with radius r and height h, its surface area S and volume V can be determined using the following formulas. So the surface area we saw was the area of a rectangle plus 2 times the area of a circle. So we get 2 pi times the radius times the height plus 2 pi r squared. To compute the volume of the circular cylinder, we need to take pi r squared and multiply that by h. Well, I want to look at some possible surface areas for a circular cylinder of volume 54 pi. Now you might ask, why would I even care what are some different possible surface areas for a circular cylinder of volume 54 pi? In an application sense, we could think, well, perhaps a company is trying to package something that has a volume of 54 pi, but to save money on packaging, they want to come up with the smallest possible surface area. Now my number 54 pi is probably not a very realistic volume. We're probably not going to measure volumes of 54 pi. Pi is an irrational number. But I've chosen this volume to make it easier to see the numbers in my computations in deciding a given radius, what's the height and what's the surface area. So I'm going to start with a radius of 1. If I have a radius of 1 and I know the volume's 54 pi, the formula for volume is pi r squared times h. Well, 1 squared is 1, so I've got pi times 1 times h. That has to equal 54 pi. So the height is going to have to be 54 in order to give me a volume of 54 pi. Now if I take 2 pi times the radius times the height, that's going to be 2 pi times 1 times 54. That's 108 pi. To that I'm adding 2 pi times the radius squared, so 2 pi times 1 squared. 2 times 1 is 1, 2, and the pi is there, so we have 2 pi. So 108 pi plus 2 pi is 110 pi. Next I'm going to look at a radius of 2. If the radius is 2, again looking at my formula, pi times the radius squared times the height gives me the volume. 2 squared is 4, so I've got pi times 4 times h has to equal 54 pi. So I just need to decide what do I need to multiply by 4 to get 54. That number is 13.5. The surface area turns out to be 62 pi. If I have a radius of 3, the height would have to be 6 to give me a volume of 54 pi. And the surface area turns out to be 54 pi. If I have a radius of 4, the height would have to be 3.375 to have a volume of 54 pi. Here the surface area turns out to be 59 pi. If I have a radius of 5, the height would have to be 2.16 to give me a volume of 54 pi. And the surface area here turns out to be 71.6 pi. Now we've only looked at a few examples in this table, but comparing the surface areas, I see that the numbers for the surface areas start going downwards at the beginning of the table and then start going back up. So it looks like based on just these few values that perhaps it would be best for this company to choose a radius of 3 in order to get the smallest surface area, in order to have the least cost in producing the packaging for whatever liquid they have that has a volume of 54 pi. Well, we've just looked at a whole lot of formulas. Most of these formulas are summarized for you in your book. You don't need to memorize all of these formulas. What you do need to make sure you do is check with your instructor to find out which formulas you do need to memorize. If there are a lot of formulas that your instructor expects you to memorize, make up some flashcards with some of these formulas. Use those to help you practice and memorize the formulas that you do need to memorize. Now this is the end of my part of the lesson on three-dimensional geometry. Now I'm going to turn this over to Anne, who's going to look at some applications of geometry.
So in this final part of the lesson, we're going to talk about problem solving using the geometric formulas that Steve and Candace introduced to you in the first two parts of this lesson. We're going to solve three problems. The first will ask, how much paint does Maria need? The second, how much does a leaded glass window cost? And the third, what is the best package for cotton balls? When we're finished solving these three problems, we're going to summarize some of the key ideas we used while solving these problems. So let's first turn to Maria and think about her painting project. Maria is painting the ceiling of her studio apartment jet black. The folks at the paint store told her that she will need to use 3 coats and that 1 quart of paint covers 75 square feet. Maria measured her studio, and the measurements are shown in Figure 1. How much paint does Maria need for the project? So here's the figure that shows the dimensions in Maria's studio. And when we're tackling a problem like this, the first thing we really want to look at is the geometry. So what shapes are visible in the sketch of the studio? Well, I've taken away all the measurements so we can just look at the shapes. The main part of her studio is a rectangle, but the rectangle is oriented so that the long side is vertical. She also has something that appears to be a bay window in her studio, and that's a trapezoidal shape, except the orientation has the parallel sides so that they are vertical. So we have the rectangular part and the trapezoidal part of her studio. So now that we've looked at the geometry of the problem, let's think about what formulas will be needed to solve this problem. We're trying to figure out how much paint Maria needs to cover her ceiling. This is going to be an area problem, so we're going to need the formula for the area of a rectangle and the area of a trapezoid. So the area of a rectangle is the length times width. The area of a trapezoid is 1/2 the height times the sum of the bases. So let's bring back the dimensions into the drawing and write down some numbers representing all of these measurements. So for the rectangle, it's fairly straightforward. The length of the rectangle is 18 feet and the width is 9 feet. So let's record these measurements. The length is 18 feet. The width is 9 feet. Now let's look at the trapezoid. One side of the trapezoid is clearly labeled as 4 feet. So one base is 4 feet. We need to figure out the length of the second base. Well, if I look at the measurements that Maria has taken, she's measured the distance from one side of her studio to the beginning of the bay window. And it's the same on both sides of the window. So the entire length of the studio is 18 feet, and we have 6 feet on either side of the bay window. So the second base of the trapezoid is 6 feet. So we have one base is 4 feet, and the second base is 6 feet. Finally, we need to determine the height of the trapezoid. So the height is the distance between the two bases, and Maria hasn't labeled it right here in the drawing. But if we look, Maria has indicated that the measurement from one side of her studio to the bay window, the end of the bay window here, is 12 feet, but the width of the studio is only 9 feet. So the height of the trapezoid is 3 feet. So we have all the information we need to calculate the measure of Maria's ceiling. So on this slide, I've just recorded all of that we wrote down. Let's do the calculation. We need to calculate the measure of Maria's ceiling. So I'm going to just add up the area of the rectangle to the area of the trapezoid. So the measure of the area of Maria's ceiling is, and let me perform the calculation. It's going to be 18 feet times 9 feet, that's the area of the rectangular portion of the studio, plus 1/2 the height of the trapezoid times the sum of the bases. So when I look at what I've written here, I see that the units work. I have feet times feet in the first term, that's square feet. And I have feet plus feet, that's feet, times feet, which is also square feet. Square feet plus square feet confirms that I'm finding an area. So now let me pull out a calculator to perform this computation. So I have 18 times 9 plus 1/2 times 3 times 10. I just added that 4 plus 6, and I get 177. So the measure of the area of Maria's ceiling is 177 square feet. Still have some more things to think about before we can calculate how much paint Maria needs. So the people at the paint store told Maria she was going to need 3 coats of paint. So she has to cover 177 square feet 3 times. So Maria needs enough paint to cover 3 times 177 square feet, which is, let's perform that calculation, 531 square feet. Okay, so we know how much needs to be covered by the paint she's buying. Now let's go back to the problem statement. We were told that 1 quart of paint covers 75 square feet. We need to figure out how many quarts will cover 531 square feet. I can use a proportion to solve this problem. So I'm going to define my unknown, which is going to be how much paint Maria needs. So I'm going to let Q represent the number of quarts of paint Maria needs for the project. And I can write a proportion to solve for Q. I know, for example, that 1 quart of paint covers 75 square feet. That should be proportional to the Q quarts that Maria needs and the 531 square feet she needs to cover. Now I just included the units here so we could see that we're comparing 2 rates, but when I solve the proportion I'm going to lose the units. So let's solve this proportion. If I cross multiply, I end up with 75Q equals 531. Dividing both sides by 75, I get Q equals 531 divided by 75. Let's calculate how many quarts of paint Maria needs. So 531 divided by 75 is 7.08. So Maria needs 7.08 quarts of paint to cover her ceiling. Now she can't walk into the store and order 7.08 quarts, so she has to make a decision. Is she going to buy just 7 quarts and maybe not get the coverage she needs? Or is she going to buy 8 quarts to make sure she has plenty of paint for the project? Well, that's really going to be a decision Maria's going to have to make on her own. But if she bought the paint in gallons instead, it might be a little bit cheaper. And 8 quarts is 2 gallons. So perhaps a wise thing to do would just be to buy 2 gallons of paint rather than 8 quarts. So Maria could buy 2 gallons of paint for her project. So we've answered one of our 3 questions. Second problem, how much does a leaded glass window cost? We're going to see it's going to be quite a bit. A glazier, Ahmad, is installing a lead glass window in a frame with the dimensions shown in Figure 2. Ahmad can only purchase leaded glass in rectangular sheets at a cost of $90 per square foot. How much glass does he need to purchase? What is the cost? How much glass will be wasted? So here's a picture of the window that Ahmad is working with. We can see that it's made up of a rectangular portion and a circular looking portion, but we're only interested in the top part of the circle. So we have a semicircle on top of a rectangle. Now, Ahmad is buying the glass in a rectangular sheet. So we need to figure out the size of the rectangle this window will fit into. So the first thing we need to figure out is the size of this sheet. We see that the width of this rectangular sheet of glass is 2.5 feet. But we only have part of the length measured in this figure. But the top part of the figure is a semicircle. We know the diameter of the semicircle is 2.5 feet. So we could calculate that the radius is half of that, or 1.25 feet. So I'm just going to draw that in here, that the radius is 1.25 feet. So when I add up those 2 measurements, the 3.75 and 1.25, this length of the rectangular piece of glass is 5 feet. Ahmad needs to buy a sheet of glass that is 5 feet by 2.5 feet. So we've answered the first of the 3 questions. Now we need to figure out what is the cost of the glass. Well, we're told that the unit cost is $90 per square foot. So we need to figure out how many square feet of glass Ahmad is buying. Well, we just need to calculate the area of that rectangle. So Ahmad is buying 5 feet times 2.5 feet, which is 12.5 square feet of glass. So to calculate the cost, I'm going to multiply the 12.5 square feet of glass by the unit cost. So $90 per square foot times 12.5 square feet. Notice the units I'm going to end up with are just dollars, which is what I want. So I have 90 times 12.5. That's $1,125. As I promised, the leaded glass is very expensive, so the glass costs $1,125. So since it's so expensive, we want to think about how much glass is being wasted. Ahmad has purchased 12.5 square feet of this glass. Let's think about what was wasted. Here's the piece of glass he purchased, and this region that I've shaded in represents the waste. So to figure out the amount of waste, I'm going to take away from 12.5 square feet the actual area of the window. So to calculate the area of the window, I'm going to need to calculate the area of the rectangular portion and the area of the semicircular portion and add those 2 areas together. So let me calculate the area of the window. So I'm going to start with the area of the rectangle. So that's going to be 3.75 feet times 2.5 feet. And now I need half the area of a circle. Well, the formula for the area of a circle is pi r squared. And I just need 1/2 of that. So I'm going to add in 1/2 the area of the circle. Well, what's the radius of the circle? Earlier we said it was 1.25 feet. So I have 1.25 feet squared. So now let me perform this calculation to see how much, what the area of the window is. So I have 3.75 times 2.5 plus 1/2 times, now my calculator doesn't have a pi key, so I'm going to use the approximation 3.14 times the radius squared, so that's 1.25 squared, that equals about 11.8. So this is about 11.8 square feet. So to calculate the waste, I'm going to subtract this from the amount of glass that Ahmad purchased. So the amount of waste is 12.5 square feet minus 11.8 square feet, which equals 0.7 square feet. And if we like, we can multiply that by the unit cost to see how much money was wasted as well. Okay, let's look at our last application problem. An industrial engineering firm is trying to decide between two container designs for packaging cotton balls. All the parts of the container are made from the same plastic. The designs are shown in figures 3 and 4. We want to determine which package is the best choice for the cotton ball company and justify our choice. So here's the first package option. It's a package for cotton balls, but it might look more like packaging for deodorant. But this is the shape they gave us to work with. And this is now a three-dimensional figure, and we want to sort of get a sense of the geometry first. So when I look at this figure, I see that part of it is cylindrical. The main part of this package is cylindrical. And on top of that, there's a spherical shape, but actually it's just half of a sphere. So we're dealing with a cylinder and a sphere in this problem. Here's our other packaging option. Again, probably looks more like a mailbox than a container for cotton balls, but cotton balls will fit in it quite nicely. And when I look at this package, I see the bottom part is just a rectangular box. The top part is a cylinder again, but now the cylinder is oriented in a different way than in the first packaging option, and we only see half the cylinder. So when we're thinking about the geometry of the second option, we'll be working with boxes and cylinders. So if we're comparing these two packaging options, we might want to know what's the capacity of each of these packages. That would be, what is the volume? We also might want to know how much material is needed to produce these packages. That would be a question about the surface area. So let's look at those numbers. So let's figure out the capacity of package option 1. So I'm going to need the formula for the volume of a cylinder, which is pi r squared h. When I look in my picture, the height of the cylinder is clearly labeled as 8 centimeters. I'm given the diameter of the base as 8 centimeters, so the radius will just be 4 centimeters. I also need the formula for the volume of a sphere. Now we only have half a sphere in this picture, so we're going to cut this number in half. The radius of the sphere is also going to be 4 centimeters. So let's calculate the capacity of this first package option. So I need to calculate the volume. So I'm going to call this the volume of the first option. So I'll use a subscript of 1. I'm going to calculate the volume of the cylinder. So that's going to be pi times 4 centimeters, that's the radius of the cylinder, times the height, which is 12 centimeters. And now I'm going to add only half the volume of the sphere. So I have 1/2 times 4/3 pi times r cubed, which is 4 centimeters cubed. So let me pull out my calculator to get a number here. So I have pi, again I need to use an approximation, times 4 squared times 12, and now I'm going to add half the volume of the sphere, so that's 1/2 times, I'm going to enter 4/3 in parentheses. Now I'm going to multiply that by my approximation of pi, 3.14, and finally multiply that all by the radius cubed. So I have a key here, x to the a, so I enter my power, and I get about 737 cubic centimeters. So now let's look at the capacity of the other package option. So here we need the formula for the volume of a cylinder again, but now we're just going to use half of it because we just have half a cylinder lying on top of this box, and the formula for the volume of the box, which is just length times width times height. So it's pretty straightforward. So let's write down what we'll need to calculate here. So the volume for option 2 is going to be half the volume of a cylinder, so 1/2 pi. Now let's look at the radius of the cylinder. This side of the box is the diameter of the cylinder, which is 8 centimeters. So again, we have a radius of 4 centimeters. Times the height of the cylinder. Well, the height of the cylinder is horizontal this time, and that's 10 centimeters. And now I'm going to add in the volume of the box, which is just 6 centimeters times 8 centimeters times 10 centimeters. So let's calculate this capacity. So I have 1/2 times pi times the radius squared times the height of the cylinder, 10, plus 6 times 8 times 10, and that's about 731 cubic centimeters. So now we'll be able to compare the capacities of the two packaging options. Let's think about the amount of packaging needed for each option. So here we need to calculate the surface area. The surface area for a cylinder is 2 pi r squared plus 2 pi r h. Pi r squared is this area of the bottom of the cylinder and the top of the cylinder. But in our package, we only have to consider material for the bottom of the cylinder. So what we're going to use is just pi r squared for this first term rather than 2 pi r squared. The formula for the surface area of a sphere is 4 pi r squared. Again, we just need to calculate the surface area of half a sphere. So when I'm calculating the surface area of my package, I'm going to take this into account. So let's write down what we need to calculate to find the surface area. So I'm going to call this S sub 1 for the surface area of option 1. So I'm just going to have pi r squared instead of 2 pi r squared. Now the 2 pi r h, that's the surface area of the sides, and I need all of that. So that's 2 pi times 4 centimeters times 12 centimeters. And I'm going to add to that half the surface area of the sphere. So let's perform this calculation. So I have pi times 4 squared plus 2 times pi times 4 times 12 plus 1/2 of 4, that's 2, times pi times 4 squared. That's about 452 square centimeters. So we almost have enough information to answer this question. Let's finally look at how much packaging material we need for option 2. So the formula for the surface area of a box is this formula here, but for our box, we have to consider the front and the back and the 2 sides, but we just have one bottom to consider, so we just need 1 of the length times width. Again, we have the formula for the surface area of a cylinder, and we're just going to use half of this because we only have 1/2 of a cylinder in our drawing. So let's fill in what we need to calculate for our surface area of option 2. So I just need 1 length times width, so that's 8 centimeters times 10 centimeters, plus 2 times the length times the height. The length times the height I see is 60, so I'm just going to go ahead and write 120 square centimeters. The height times the width is 48. I need 2 of those, so I'm just going to write 96 square centimeters. And when I take 1/2 of the formula for the surface area of a cylinder, I can just divide by 2, and I'm left with pi r squared plus pi r h. So I have pi, the radius of our cylinder is 4 centimeters squared, plus pi times 4 centimeters times the height, which is 8 centimeters. So let me calculate this value. So I have 8 times 10 plus 120 plus 96 plus pi times 4 squared plus pi times the radius times the height of my cylinder, and I have an 8 written there, but looking back I see it's actually 10, so this should be a 10, and that's about 472 square centimeters. And so let me just change this to a 10. So this should have been 10 centimeters. And I have 472 square centimeters of surface area on this package. Whew, what a lot of calculations. But now we can determine which package might be the best option. So the capacity of package option 1 was about 737 cubic centimeters, and about 452 square centimeters of packaging material is needed. Whereas with option 2, the capacity was about 731 cubic centimeters, which is less, and more packaging material is needed, 472 square centimeters. So package 1 has a greater capacity and less material is needed. So it seems like the reasonable choice would be package option 1. So package option 1 is a reasonable choice since the capacity is greater and less material is required. A lot of work, but we made a fairly sound judgment after all those calculations. So let's summarize some of the ideas that we've discussed. We did 3 applications, and there were some keys to applying these geometry formulas that we could use in similar applications. So the first thing we want to do is identify the 2- or 3-dimensional shapes present in the problem. Is the shape a basic shape, or is it a combination of basic shapes? In all the examples we worked today, the geometry we were working with was a combination of basic shapes. That happens a lot in applications. Does the problem require us to think about the boundary of the shape, perimeter or surface area, for example, or the space enclosed by the boundary? Do we have to calculate area or volume? And finally, is there any additional information that needs to be considered in the problem independent of the geometry? None of these problems said, find the volume of the object. They were all phrased in different ways, and we used volume, we used area, we used surface area to solve the problems, but we needed to bring in additional information in order to answer the question. So that finishes up Lesson 12.